Good morning, students. I want to make this one nice and short and sweet. So let me just give you a couple examples of things that might be useful on the quiz. Anyway, let's start with if we have to find the partial derivatives f sub x and f sub y of a function f of x and y equals, say, x times the sine of x times y. So, f sub x means that we treat x like it's a variable and we treat y like it's just a constant. So in some ways we could just replace y with, like, if I made this 4, so if I had the function x times the sine of x times 4, we would know what to do. And we just do that and then just replace the 4 with the y. So this is a product rule thing, so I need to actually do the product. So derivative of x is 1 times sine of x times 4, but 4 instead of that I'm going to say y, and then I say plus, and then this is the first thing times the derivative of the second. So the derivative of the second, so this is going to be cosine of x times 4, which 4 becomes a y, times, and then I have to chain on the derivative of x times 4, which in that case is 4, but our 4 becomes a y. Sorry for writing messy, but we'll just hide that little bit. So, because it didn't really matter and it went away. So just to rewrite this nice and clear, f of x equals sine x times y plus x cosine x times y times y. This last y again came from the chain rule. Excellent. So f sub y, again we're just going to this time pretend that x is just a constant. So again here, maybe I can write this a little better. Off to a side, if I were to pretend x was 4, then I would have 4 sine 4y. And if y was my variable, I would know how to take the derivative of this. So this 4 out front just goes for a ride, but 4 is x in this case. And then I need to take the sine becomes a cosine. Inside stays the same, but my 4 is an x times y. And then I'd have to chain on the 4, but again 4 is an x. So in this case I could easily just rewrite it with this x in front, and this is x squared cosine x y. Cool. So that's that. Moving on. So if we were given a function, say, I don't know, 1 over x, but we were given it piecewise. So we're given it this if x is not 0, and let's say it's 8 if x, if x equals 0. We'll give that a function, we'll call it g. Okay, so if we were to graph this, it would look something like that, and right at 0 it has a value of 8. Okay, and we can see obviously this is not continuous, because if I try to draw my finger along the line, I don't end up going through that point. I'd have to lift my pencil up to go through this point, and then I'd have to lift it up again to go that way. Remember, discontinuities can come in different forms. I can have a hole. I can have an asymptote. I can have an asymptote where they go both the same direction. So all of those I have to lift my pencil up. Drawing, lift my pencil up. Okay, so in multiple dimensions, essentially it just has to be continuous on every path that I would draw with my pencil. So if we have a more complicated function, let's say h of x and y that equals, let's say it's 1 over x plus y, and let's raise each of those to the 4th power. And that's if x, y is not 0, 0. Okay. And then we're going to say it's 8 again if x comma y does equal 0, 0. Okay, so now we could just see that if I tried to draw a line, I could actually, in this particular case, because this thing goes to 0, so I'm dividing by 0, and it blows up. So I kind of get one of those functions where I get, oops, sorry, I'll move that over a bit here. So I get a function where as I get closer and closer, it blows up and becomes more and more infinite. But then right at 0, somehow it's 8. So I'd have to pick my pencil up. The trick is that if I want to show that this is discontinuous at this point, I can use any line I want whatsoever. So if my function has a hole in it, it doesn't matter which way I draw in. I can go in on a wiggle. I could go in on a straight line. However I want to do it. I can go in any direction. And by going in that direction, I'm going to encounter one of these discontinuous situations. So if I want to show it it's discontinuous, it shows it's enough to pick any line that goes through that point that shows that it's discontinuous. So the trick is to pick the easiest line possible. In this case, I think one of the easiest lines is, what if we just said we let y equals 0 and we came in on the x-axis? So if we were to trace this surface, so it's a two-dimensional surface as x and y, we could trace it in on the line where y is 0, and we would just get the function 1 over x to the 4th and 8. And that shows off the same discontinuity we would have up above. This was an x. This is x to the 4th, still blows up at 0. Okay. But we could also say pick the line 1 over, what if we restrict to the case where x equals y? So we're coming in on a diagonal in this way. Well, then I could reduce this to saying it's 2x to the 4th. And if I do that and 8, again, because I'm dividing by 0, this blows up. This is a symmetric sort of function, so it blows up no matter what direction I come in. Some functions are a little bit picky. I'm trying to show that off. If I have a piece of paper, if that paper has, like, say, a hole in it, put a hole in my piece of paper. So I got a piece of paper with a hole in it. My surface, my function, could be anything I want, no matter what I do. If I go in towards the hole, there's a hole. So any path whatsoever goes through has a hole and comes out. Kind of like this situation here. And it wouldn't matter which path I took, that hole is always going to be on there. On the other hand, I could have some functions where, let's say it actually goes sort of like this. So I could have a function that looks like this. And if I say this point down here is not included, but this top one is, I could draw a line straight across the very top of this. And that line I didn't have to lift my pencil up. But if I try and draw a line across this way, boom, I'd have to lift my pencil up in order to go across the gap. Hopefully that shows that off somewhat. So functions can be like this, where it depends on the line. Functions can be like this, where there's a hole, and it doesn't depend on which line or path I come in on. Other functions that can blow up and go to infinity at a spot, and it wouldn't matter what path I go in on. Some functions can actually blow up and go to both infinity and negative infinity in a similar way to this. I know that gets confusing, but essentially, just imagine once we apply the conditions, if I say that x equals y, I can then reduce the function, and then this discontinuous the same way as in previous classes. Hope that helps. Bye.